Historically, the biggest empires always had the biggest navies or the biggest armies, the most ships, the most men, or both. And in the modern age, science and industry have repeatedly pushed the limits of men, technology, and imagination in the pursuit of that power. More often, not by creating bigger armies, but bigger weapons. From aircraft that defy gravity, tanks to field guns, bombers to battleships. The destructive capability of the machinery of war develops with each decade, each unique in their own way. The machines in this episode share two common traits. They are big and they are powerful. In World War I, guns began to assume monumental proportions. Big Bertha, the German siegebreaker, could hurl an 800-kilogram projectile 13 kilometers and was used to devastating effect in the early stages of World War I. But during World War II, a class of even larger supercannons emerged, and their psychological effect on the men facing them meant that, like Bertha, they all had personalized names. And one of the biggest was called Annie. Annie was one of 25 massive railway guns designed and built by the famous German Krupp Steelworks prior to the commencement of World War II. Designated the K-5, they were developed to deliver shells capable of destroying the French border fortifications known as the Maginot Line.
The first objective was to deliver a large projectile containing a large amount of explosive to the target. The second objective was to provide range, and some of the quarter-of-a-ton projectiles were able to reach 50 kilometers.
Although they never saw service on the Maginot Line, they were involved in a variety of sieges. And for Annie, that most famously took place during the American invasion of the Italian coastal town of Anzio in early 1944. Annie was one of two K-5s moved and hidden in rail tunnels, 18 miles above the coastline where the Americans had landed. From this vantage point, over 2 months, the pair rained down their massive exploding shells on the 70,000 Allied troops trying to break out of the established beachhead. It was during this time that the train-like sound the huge shells made as they passed overhead earned the guns the nicknames Anzio Annie and the Anzio Express. And the K-5's 288mm caliber barrel was rifled with 12 7mm grooves, making it not just big, but extremely accurate. Each K-5 railway battery consisted of 2 guns. Each gun had its own train, with engine and 6 rail cars. Ultimately, it was that size that proved her downfall.
For a railway gun, you had to lay tracks to get it to its destination. Now, not only was that intensive in terms of manpower, but also, inadvertently, what you did was, when you were laying these tracks, you were providing a path for the Allied bombers to track where that railway gun actually was. So its survivability was put into question by virtue of the fact of the tracks that it was running on.
The railway gun's great advantage of being able to use existing infrastructure to besiege armies was, paradoxically, its Achilles heel. when on January 20th, 1953, at the height of the Cold War, former World War II General Dwight D. Eisenhower became President of the United States. His inauguration parade included 65 bands, floats from the then 50 states of the Union, 22,000 servicemen and women, 350 horses, and a gun. A brand new 280mm cannon.
In the early 50s, they were exploring how to deliver nuclear payloads. And there was a series of tests in Nevada where they tested a variety of different delivery systems.
One of which was the M65 howitzer. With missiles capable of delivering atomic warheads, the most powerful weapons on the planet, in the control of the U.S. Air Force, the U.S. Army felt it too should have a weapon of similar force. And when in 1949, the U.S. Atomic Energy Commission announced the development of a 280mm caliber nuclear projectile, the Army set to work developing a mechanism to deliver it. The result was a self-propelled gun with an overall weight of 78 tons, a length of 26 meters, and a width of 5 meters. Advances in mechanics meant that, once in position, Atomic Annie could be set up in 15 minutes. And in May 1953, in the deserts of Nevada, the weapon was tested.
And they did actually fire an 800-pound nuclear shell from a 280mm artillery piece 7 miles in the Nevada desert to explode as a nuclear device. It's the only time, certainly in the Western world, that a nuclear shell had been delivered by a cannon.
Nine M65s were deployed in Europe to counter the Soviet threat. But Atomic Annie, like Anzio Annie, was a transportation nightmare. On the road, it resembled a large fire engine, with 2 prime movers using independent steering systems, one positioned at either end of the gun carriage. Its propensity to tip over earned it another less favorable nickname, the Widowmaker. Evolution sometimes heads in a direction that doesn't quite work, and nuclear technology did not find a natural place fired from a gun. As the end of 1962 approached, the idea of the stately and visible progress of an atomic cannon moving across the world as a crucial influence had passed. New weapons had been developed, and the Atomic Annies joined their cousins, the K-5s, in retirement.
All were withdrawn from service, along with their 80-odd shells constructed for them.
What history has shown us is that power is not always about sheer size. The punch of a behemoth doesn't necessarily have to come from a behemoth. And in the case of the M777, while it is still a large weapon, 155mm in caliber, and with an overall length of 10 meters, the focus of its development was on reducing its weight, which makes it extremely powerful.
And it means that the M777 could be transported in a larger range of helicopters than its previous counterpart. And so, in that regard, it can be a much more deadly weapon because the military can get it to where it needs to be quickly.
The M777 tips the scales at just over 4 tons. To achieve this low weight, it applies the latest advances in metallurgical science, and its construction makes extensive use of a rare metal that has found numerous applications in the modern machinery of war: titanium.
Now, titanium has a density which is about half that of steel, but it's a very strong material. So it means that you can reduce the weight of your structure, but at the same time maintain strength that you need when you're dealing with the high shock forces when the gun fires projectiles.
Everything about the M777 is a stark example of more for less. It's operated by a crew of 5. Anzio Annie had a crew of 82. The M777 can rapid fire 5 rounds per minute. Annie fired one every 5 minutes. And while Annie was accurate, modern shells like the Excalibur take accuracy to a new level.
So the Excalibur is a shell which has a little sort of motor that kind of deploys fins on firing and can actually use these fins to intelligently guide the shell to its target.
A lightweight behemoth with incredible power and accuracy. One of the few things the M777 can't do is move itself. And a barrage is of little use if you can't press your advantage. To do that, you need to get up close. Necessity, they say, is the mother of invention. The mass of wire, mud, trenches, and modern weaponry on the Western Front during World War I had led to an appallingly costly stalemate, where success was measured not in kilometers gained, but mere meters. But on the 8th of August 1918, at the Battle of Amiens, on a single day, the Allied forces moved 13 kilometers across German-held territory. And on that day, the battlefield hummed with the sound of over 550 of what would prove to be perhaps the defining weapon of the war. Tanks.
When the British were designing the tank in 1915, 1916, they were aware of the nature of trench warfare on the Western Front. And the reason for this large track design in that lozenge shape of the first tanks was to give the tank mobility. So if it came to the trench lines, if they were able to break through, is that they'll be able to cross them without falling into a trench and getting irrevocably bogged.
The 28-ton rhomboid-shaped Mark I tank first saw service on the Somme on the 15th of September 1916 and was not a huge success. Mechanical problems from what proved to be an underpowered and unreliable 78-kilowatt engine and crews inexperienced in handling the new weapon compromised the performance of the few that made it to the battlefield. And they were slow.
It actually was slower than an infantryman walking, which meant that rather than being the tanks advancing and the troops coming behind the tanks, it often meant that the troops went far in advance of the tank, which found it hard to keep up.
Noise inside the tank made it difficult to communicate, and as a result, some became hopelessly lost. Others ground to a halt, their crews rendered unconscious by the fumes of the engine, which sat in the middle of the fighting compartment without any cover or muffler. And they were prone to bogging in the muddy morass that was the Western Front. But development persisted. Adjustments to each variation were made based on combat experience. In the Mark IV, power was up to 15 kilowatts. Weight was down to 25 tons. Speed increased to 6.5 kilometers an hour. Continuous improvements that by 1918 saw the tank entrenched as a vital cog in the machinery of war.
You think of the emergence of the tank on the battlefield in the First World War. It's clunky, it's unreliable, the armour's perhaps penetrated by rifle or machine gun fire, but nonetheless it's this lumbering, terrifying beast of war you've never seen before. It has an immense psychological impact. And it becomes tactically very significant. As a soft, squishy infantryman with a rifle, you are absolutely outclassed by this giant land ship. And that remains true for decades.
And within just 2 of those decades, tank warfare reached its zenith with the outbreak of World War II and the famous German blitzkrieg tactics of 1939. A highly mobile and destructive all-arms method of fighting, led by the famous Panzer tanks. Blitzkrieg reshaped the battlefield, where previously emphasis had been on a smattering of light tanks and infantry support roles. The Allies now desperately needed medium tanks that could compete with and defeat the German panzers. But in tank design, the British had fallen well behind the game.
The British in 1918, it can fairly be said, were probably the leaders in tank design. However, the belief that tanks would be useful in European war, but probably not in the colonial warfare which the British find themselves doing in the interwar period, meant that they did not spend as much time looking at tank design as they did until probably late in the 1930s.
Outclassed and with limited time and limited resources, they turned to the Americans for salvation. They responded with the M4 Sherman, the most widely used tank by the Western Allies during the war. The design brief was simple: a medium tank with a 75mm main gun mounted in a full traverse turret. Fast enough to keep pace with the German tanks, with good all-round visibility and improved armor allocation. And it was needed almost immediately. To save time, the Americans incorporated the engine, transmission, tracks, and suspension systems of the M3 Lee medium tank. On that existing chassis, they put an all-new body with frontal armor that was not a patchwork of riveted plates, but a solid piece of cast homogeneous steel 50mm thick. To overcome the strength disadvantage of cast armor, the front armor plate was cleverly sloped to 56 degrees, creating a surface that would cause some incoming rounds to glance off. But more importantly, it increased the effective thickness of the armor on the horizontal plane to 91mm, almost doubling protection. Even so, against the heaviest of tanks, the Sherman was vulnerable.
Crews putting extra track on the front of their vehicles, they're putting extra sandbags on the front of the vehicles, and this is trying to retard an incoming armour-piercing round. Sometimes not to great effect.
Weighing close to 30 tons, the Sherman had a top speed of 40 kilometers per hour, meaning it could keep pace with its principal foe, the Panzer. And armed with a medium-velocity 75mm main gun, 2 anti-infantry machine guns, and a 50 caliber Browning anti-aircraft gun, they had the Panzer covered. But the Sherman's greatest strengths were its reliability and its numbers. Nearly 5,000 were produced, built by the giants of the American motor industry: Ford, Chrysler, and General Motors.
That whole Henry Ford type thing, the production line of cars, now applies to making a tank.
The Sherman's life was extended, seeing combat in numerous Cold War conflicts. But as anti-tank weaponry improved and the speed of warfare increased, the need arose for battlefield behemoths that were simply bigger and faster. And there are none bigger than the tank they call Whispering Death. The Cold War fueled an environment which led to the development of some of the most advanced weapon systems on the planet. And when in the 1970s, the US Army decided they needed a faster tank with exceptional firepower and unprecedented levels of crew protection, they took the best of the world's available military technology and created the M1 Abrams. Learning lessons from a variety of conflicts, they designed a tank that, despite weighing up to 70 tons in some variants, has a deceptively low profile. Standing less than 3 meters tall, the low height makes the Abrams a less obvious and less available target for enemy fire. Significant work has also been done to reduce the thermal signature of the tank, making it harder to detect. But if it is hit, it is constructed using the most advanced armor available.
The protection system of the M1 Abrams is fairly superior compared to a lot of main battle tanks. And certain variants of the M1 Abrams actually use depleted uranium in the turret. Now, depleted uranium is a very dense material, and that means it's able to provide superior levels of protection against a whole range of weapon systems.
It was also the first tank to use the British-developed Chobham armor, a complex laminate structure that combines an arrangement of ceramic blocks, metal plates, Kevlar, and open space to achieve a near-perfect blend of anti-penetration surfaces. In battle, the Abrams 120mm smoothbore main gun has been found to outrange any other tank in current service. And connected to the world's most advanced tank-based targeting system that monitors the tank's tilt, motion, and even the wind, it allows the Abrams to fire on multiple targets with accuracy while on the move. But what truly sets the Abrams apart is its speed, which can exceed 70 kilometers per hour. To achieve this, it uses a distinctive power source.
The use of the gas turbine engine in the M1 Abrams is fairly unique to main battle tanks. And the reason why they use a gas turbine is simply to reduce the noise and to give it the power it needs to accelerate such a heavy vehicle. This vehicle weighs up to 70 tons with certain variants, and so it's a very heavy piece of military equipment, and you need a substantial means of driving that forward.
It is the whisper-quiet gas turbine that has given the M1 its nickname. A power source that is normally associated with a very different kind of battlefield behemoth: aircraft. On the 6th of August, 1945, an event took place that would change the world forever. The heaviest bomber of World War II delivered a device that would create the biggest explosion mankind had ever experienced. Less than 30 years previously, heavier-than aircraft had been little more than curiosities. But the aircraft that carried that fateful payload in August 1945 was a far cry from the timber and fabric of World War I. It was a heavy bomber that revolutionized military and civilian aviation. Militaries always want aircraft with increased speed and payload, but in World War II, what the Americans desperately needed was one with greater range to deal with the huge distances covered in the war in the Pacific. To achieve a lethal combination of speed, payload, and range, they based their designs on an aircraft that was already the supreme bomber of World War II, the B-17 Flying Fortress, and built the largest, most complex aircraft that had ever gone into production.
The Flying Fortress was a very capable aeroplane, but it was firmly rooted in the 30s, and it had been developed as far as it could realistically go. With the B-29, they designed it to do everything a Flying Fortress could do and do it all better.
The B-29 was a combination of cutting-edge technology and devastating firepower, wrapped in a massive package. Fitted with 4 of the largest radial engines manufactured in the United States, the supercharged 18-cylinder Wright R-3350 The superfortress had a top speed of over 550 kilometers per hour and a combat range of 5,220 kilometers, double that of the B-17. And it was designed for sustained flight at what was then dangerously high altitude. As you ascend, temperature drops 1 degree per 300 meters. Without heating and oxygen, anoxia can result in death within 10 minutes at altitudes over 7,500 meters. To overcome this, the B-29 became the first production aircraft to feature a fully sealed and pressurized cabin.
It allowed them to fly routinely over 35,000 feet, where the air is thinner and therefore you can fly faster without putting as much strain on the engines to maintain the speed.
The B-29 was in every way a technological marvel. A systems-driven aircraft with over 10 kilometers of electrical cabling, part of which fed a state-of-the-art analog firing system that remotely trained the aircraft's 5 gun turrets on incoming targets, compensating for speed, gravity, and atmospheric pressure. Intercontinental range, payload, and versatility made the B-29 a game-changer that not only helped end the war, but paved the way for both the Americans and the Soviets to pursue even grander designs. Designs that would allow them to deploy greater payloads to war zones with unparalleled speed. It started a game of brinkmanship, a race to be the biggest, a race the Soviets would ultimately win. During the latter stages of the Cold War, when the Americans unveiled the massive C-5 Galaxy transport, the Soviets immediately countered and produced an aircraft that remains the largest airborne military transport vehicle in the world today. Known by NATO as the Condor, it is the Antonov AN-124. Big machines need a big aircraft to lift them. Designed to carry the largest Soviet tanks, troops, and support equipment and deliver them to a hotspot quickly, the AN-124 has a maximum takeoff weight of 405 tons with a payload of 150 tons. To put those weights into perspective, it can carry 2 fully loaded B-29s, throw in a fully loaded B-17 for good measure, and still have room to spare.
The design of large transport aircraft require the right combination of the design of a fuselage that can accommodate the potential payloads that may be required during its operation. Included in that is the access to the payload.
With a fuselage close to 70 meters in length and 21 meters in height, creating a cargo space 36 meters long and 6.4 meters wide, comparable in size to a bowling green, the sheer size of the aircraft presents a unique design challenge.
Larger fuselage will affect the aerodynamics of the aircraft, it will increase the drag of the aircraft, and so you have to balance that with wings that are large enough to generate enough lift, and also, quite principally, the engines that develop enough thrust to lift these aircraft.
To generate that required lift, the AN-124 has a wingspan of 73 meters. And with an upper deck that can accommodate 88 fully equipped soldiers, it can deploy a small army at over 1,000 kilometers per hour. The AN-124 is big and fast, but on its own, not lethal. The Tupolev Tu-160, on the other hand, is all three. Known by the NATO codename Black Jack, or the White Swan in Russia, the Tu-160 was the last bomber aircraft produced by the Soviet Union before its collapse, and is the largest jet-powered swing-wing combat aircraft ever to enter service. An aircraft again born of the military tit-for-tat that was the Cold War. when the Americans began developing a similar aircraft, the B-1.
The Americans were developing a supersonic swing-wing bomber that could quickly penetrate Soviet airspace. During that development, interestingly, the Americans actually decided perhaps that need wasn't there, and so the Americans actually cancelled the B-1A program. The Russians, however, continued with the Blackjack and developed that aircraft into a very capable, very high-speed, penetrating bomber.
All supersonic aircraft have swept wings. Put simply, the faster you go, the less wing area you need to generate lift. But at low speeds, that lift is greatly reduced. The engineering challenge was to produce an aircraft with enough lift to raise a serious payload, but one which could also reach speeds comparable to a modern fighter jet.
And one solution for that is so-called swing wings. During low-speed operation at takeoff and when you return for landing, the wings are swept forward so that they are what we call very high aspect ratio wings. And that configuration of wing is optimized to generate lift very efficiently, especially at low speeds.
The variable geometry outer tapered wings of the White Swan are able to be swept back from 20 degrees to 65 degrees, providing high-performance flight characteristics at both supersonic and subsonic speeds. And the tail surfaces, horizontal and vertical, are one piece and all moving for improved low-speed control. Equipped with 4 of the most powerful engines ever fitted to an aircraft, the Tu-160, which weighs 275 tons fully loaded, manages an extraordinary top speed of 2,200 kilometers per hour and climbs at a rate of 70 meters per second to a service ceiling of 16,000 meters. But while a behemoth in the air or on the land can be measured in terms of bowling greens, at sea, the word behemoth takes on a whole other meaning. For centuries, a nation's naval strength determined its place in the world. And as the centuries passed, ships slowly increased in size. But the Industrial Revolution sped that growth. Engines created a new source of power. Power gave rise to bigger ships with heavier guns, and heavier guns led to heavier armor. And in the early 1900s, a naval arms race led to the creation of ocean-going behemoths of such size that they defied imagination. Battleships.
The battleship really, I suppose you could say, reached its zenith during World War I. It was a large steel ship, heavily armoured, fitted with big guns which could sling tons of shells towards an enemy battleship. Since then, battleships continued to be used through the Second World War, but more as large gun platforms than the traditional engagement between 2 battle fleets steaming in parallel, endeavouring to sink each other.
And in the Second World War, one of the biggest of those gun platforms was the American Iowa class. World War II saw a shift in the shape of naval warfare. The Americans' new and fast Essex-class aircraft carriers had stolen the battleship's mantle as the capital ships of the fleet. But they needed vessels that could protect them at speeds in excess of 30 knots. The design challenge was to develop a battleship fast enough to keep pace, while also providing the firepower to combat the heavy Japanese vessels already constructed. At over 270 meters in length, and with a beam of 33 meters, everything about the Iowa class was big. 8 water tube boilers, feeding 4 advanced steam turbines, gave the Iowa a top speed of over 33 knots. And to guard against torpedoes, the Iowa class had a hull design that included an internal bulge, consisting of 4 longitudinal bulkheads behind the outer hull plating. With a depth of 5.5 meters, designed to absorb the energy of a torpedo warhead, protecting the superstructure. But a battleship is nothing without big guns, and the Iowa class carried 9 massive Mark 7 main guns, each with a caliber of 410 millimeters. Perhaps the most well-known of the Iowa class was the USS Missouri, with the Japanese famously signing the surrender ending World War II on her deck on the 2nd of September 1945. Decommissioned a number of times before being brought back into service, first in Korea in the 1950s and again in the 60s, where her massive guns provided extra firepower in Vietnam. The Missouri was finally decommissioned in 1992 after being resurrected yet again during the First Gulf War. But not all battleships were survivors. Hitler, at one time, referred to the First World War German fleet as a romantic plaything, a parade piece. If Germany were to fight again, under Hitler, they would have a navy to be reckoned with. And by 1939, Germany boasted a modern fleet of staggering proportions. And the centerpiece of that fleet were 2 50,000-ton battleships, the Bismarck and the Tirpitz. The largest battleship class in Europe, these 250-meter-long behemoths had a top speed of 30 knots and a range in excess of 16,430 kilometers. In the Battle of Denmark Strait on the 24th of May, 1941, the Bismarck and the Prinz Eugen engaged the British battleships, the Prince of Wales and the Hood. After only 8 minutes of firing, the Hood took a hit in her rear ammunition magazine, and 100 tons of cordite exploded, breaking the ship's back. She quickly sunk, taking all but 3 of her crew of 1,419 men with her. The Prince of Wales was also damaged and laid a smokescreen to cover her withdrawal. In those 8 minutes, Bismarck had fired 93 armor-piercing shells and had been hit by 3 shells in return. One had struck the forecastle, and 2,000 tons of water flooded the ship, contaminating fuel oil stored in the bow. Forced to change course to seek repairs, the Bismarck was pursued by the Royal Navy. Over the ensuing 2 days, the German vessel took a surprising number of hits and still managed to evade her pursuers. And it was armor that was the key to the Bismarck's survival. Nearly half of the vessel's overall weight constituted protection to vital areas. At the belt line, it reached 320 millimeters thick. On the decks, 120 millimeters. And the main gun turrets were shrouded by steel 360 millimeters thick. What did it for her in the end were the machines that spelled the end of the battleship as a machine of war: aircraft. On the 26th of May, a flight of 15 Swordfish torpedo bombers launched an attack. Within just hours, the pride of the German fleet was sunk.
What's really fascinating about the action against the Bismarck was that the aircraft, the Swordfish, the most basic, simple little aircraft with torpedoes slung underneath it, operating from an aircraft carrier. I mean, the aircraft were technologically ancient.
The ship that launched those aircraft was one of a new type of warship that would hold sway for decades as one of the most powerful of all the machinery of war, and one of the biggest. The aircraft carrier. The British began using ships to carry aircraft in World War I. The first was the HMS Ark Royal, a heavily modified merchant ship that transported float planes in her hold, which were slung over the side using cranes. Despite not being a carrier as we know them, she introduced a number of features which are typical of aircraft carriers today.
An enclosed hangar, which contains the aircraft, a clear deck forward so that you could launch aircraft from there, and workshops to provide all the means of supporting those aircraft. The ship unfortunately only had a speed of about 10 knots, so she was not very capable of high-speed operations or real use as an aircraft carrier.
Those real, purpose-built aircraft carriers emerged in the 1930s. And in the early days of 1941, among the ships which gave chase to the Bismarck was one of them, also named Ark Royal, and launched in 1938. Far from being a converted merchant ship, HMS Ark Royal displayed the two most distinctive features of a modern aircraft carrier. A flat 240-meter flight deck that overhung the stern 20 meters above the waterline, and the familiar control tower island positioned on the starboard side. With armored hangars extending 3 stories below, the 50 aircraft that made up her strike weapons were raised to the deck by hydraulic lifts. Equipped with the now famous arrestor cables to catch the aircraft on landing, the Ark Royal used the latest steam catapult system to assist them at takeoff. With those aircraft comprising the Ark Royal's primary weapons, she was lightly armed. But with a top speed in excess of 30 knots, Britain's military planners believed they would be able to outrun most enemy ships if attacked. This thinking also led to the Ark Royal being relatively lightly armored. And it cost her. In November 1941, while sailing toward Gibraltar, the Ark Royal fell victim to the German U-boat U-81. Sunk by torpedoes, just as the Bismarck had been only months earlier. But where aircraft carriers really came into their own was in the vastness of the Pacific. And their experiences would change the face of warfare forever. One of the early lessons of the Second World War was that the rapid advances in aircraft performance and capabilities during the interwar years meant that command of the air became a prerequisite to success in land or sea engagements. The superior range, flexibility, and effectiveness of carrier-launched aircraft was no more ably demonstrated than on the morning of the 7th of December, 1941. When a Japanese task force that included 6 aircraft carriers attacked Pearl Harbor, and in a little over 2 hours, decimated the American Pacific Fleet. The U.S. immediately responded by declaring war on Japan and began planning a reprisal. What the Americans wished to do was attack the Japanese where they least expected it, on their own soil. And to do that, they drew on a growing understanding of the aircraft carrier's potential.
You can approach your enemy territory and exercise your influence by means of force with your aircraft from your ship. You don't need a land base. You don't need somebody else's territory to operate from. You can operate from your own ship in international waters.
The reprisal attack became known as the Doolittle Raid, and it was carried out using one of the new Yorktown-class aircraft carriers, the USS Hornet. The Hornet had a wartime complement of close to 3,000 and was capable of carrying a mix of 90 aircraft, including torpedo bombers, fighters, and dive bombers, giving her an unmatched ability to respond to all manner of situations. And in April 1942, she steamed towards Japan carrying a special unit of 16 highly modified B-25 Mitchell medium bombers, under the command of Colonel James Doolittle. Although none of the B-25 pilots, including Doolittle, had ever taken off from a carrier, on the morning of the 18th of April, in a heavy gale, all 16 aircraft launched safely, and from a distance of over 1,000 kilometers, began their journey towards Japan. The aircraft began arriving over Japanese cities at about noon, 6 hours after takeoff, and attacked military and industrial targets in Tokyo, Yokohama, and Osaka. None were shot down, but landing medium bombers on the Hornet's 245-meter flight deck would be impossible for the aircraft, which were deliberately ditched over China following the raid. All of the aircraft were lost, but all bar 11 crewmen emerged unscathed. The Doolittle raid was the first American attack on the Japanese homeland, and not only bolstered morale at home, but in demonstrating the reach of American naval and air power, it had a deep psychological effect on the enemy. It also marked the emergence of the aircraft carrier as the dominant force in the war in the Pacific. As aircraft grew in size and power, they also grew in consumption. And the Cold War prompted a desire for warships that could operate without restriction.
Now, of course, in the aircraft carrier, if you can provide the propulsive power without needing all fuel, you've got an advantage. And the nuclear reactor provides that advantage. You don't need to fuel the aircraft carrier for our own propulsion. And you can use the space which is freed up to carry fuel for the aircraft.
The first American nuclear carrier was the Enterprise class, which saw service for 50 years. It was followed by the Nimitz. The Nimitz class is over 330 meters in length, displaces 100,000 tons, and can carry its cargo of 90 aircraft, which are launched from a flight deck with a total area of over 18,000 square meters that sits 20 stories above the surrounding sea. And it cruises at 32 knots, a speed it can maintain for 25 years.
A warship does all its work at sea in any conditions, and a warship has to take the crew and the weapon systems to sea, keep the crew fed, fit, and working under any conditions, and to be able to fight under those conditions. This imposes considerable challenges on the way you design a warship and their survivability at sea.
Survivability was central to the Nimitz design, and being powered by two modern and relatively small Westinghouse nuclear reactors allows a lot of hull space to be dedicated to that survivability. As such, over 14 million liters of aviation fuel is stored on board. Added to that is the capacity to stow over 3,000 tons of ordnance. The Nimitz carries the latest in passive and active defense systems. However, the U.S. Navy still bears the scars of World War II. As a consequence, the aircraft hangars on board are divided into 3 fire bays on each level by thick steel doors that are designed to restrict the spread of fire. A feature present on all U.S. aircraft carriers since the devastating fires caused by kamikaze attacks over 70 years ago. The 10 Nimitz-class aircraft carriers, once the largest warships on the planet, are one of the most devastating of all the machinery of war. Now, however, their mantle as the largest falls to the Gerald R. Ford class. Designed like the Nimitz with a lifespan of 50 years, history suggests that her replacement will be even bigger. The ancient Chinese military strategist Sun Tzu wrote that all warfare is based on deception. And on the modern battlefield, deception means stealth. In the 21st century, being unseen to the enemy has become a dominant focus of military technology. From deadly snipers to aircraft that are invisible to the most sensitive tracking systems. From surface ships that seem to vanish, to the ever-increasing sophistication of the silent killers beneath the waves. The quest to be unseen continues to change the way we engage in battle. This is the story of stealth. The role that aircraft play in battle has changed dramatically since the First World War. No longer simply airborne observation platforms, today's aircraft are a vital part of a mobile attacking force. And to be as effective as possible, it helps to be stealthy. In the past, stealth meant a healthy dose of speed, combined with high altitude and a fancy paint job. But that fanatical drive to go faster and higher has given way to a more potent ambition. The ability to operate without forewarning, to seem to be invisible. A fifth-generation fighter, and perhaps the most capable air superiority weapon in the world. The F-22 Raptor is the product of 60 years of active stealth research. Designed as a successor to the F-15, arguably the most capable fighter of its generation, the Raptor was created to meet the threat from the Russian-built Su-35, giving the U.S. Air Force an air dominance fighter that was lethal, fast, but more importantly, almost impossible to detect.
Its principal differences to the F-15 were in two aspects. The first of those aspects was in observability, in stealth. Unlike the F-15, which had been optimized for its aerodynamic performance, the F-22 from the outset was optimized so that it could not be seen by the adversary.
So how do you make an aircraft invisible? You limit what's called its radar cross-section. As radar works on the principle of reflected radio waves, to not be seen requires a surface that refracts radar signals so that they don't bounce back to the source. To help achieve this, the F-22's outer shape is very clean. Great care has been taken to align all hard edges on the wing, tail, and engine inlet so that the radar return from any given point is aimed in a number of limited directions. This results in a few relatively large but narrow radar spikes that are difficult to detect and, if detected, almost impossible to track. Improvements in the design of radar-absorbing materials, or RAM, contribute to weight savings, making the F-22, while similar in size to the F-15, over a ton lighter. As aircraft speed increases, the infrared signature also increases due to the friction caused by air moving over the outer surface. And so an infrared topcoat is used on the F-22 to ensure that the radar and infrared signatures are balanced. Employing the latest turbofan engines, the F-22 cruises at unprecedented speeds without engaging afterburners, a prime source of heat and noise. And to further reduce the heat signature of the engines, the plane employs engine vectoring.
The integration of which combined the ability to reduce the infrared signature of the exhausts of those engines with the ability to vector that exhaust to increase the maneuverability of the aircraft at speed, in fact, to the point at which the aircraft had departed the normal flight envelope.
The result? The F-22 has a top speed of 2,300 kilometers per hour. While the Raptor may be one of the most technologically advanced machines on the planet, like much of the machinery of war, its design stems from the need to overcome the strategic importance of another invention. For the F-22, that invention is radar. In 1935, Hitler announced that he was breaking the First World War armistice agreement and was rearming Germany. Since the war, the rapid increase in airstrike capability, most notably the emergence of long-range bombers, was viewed as a dire threat. And so a race began to find a technology that was able to counter it. In the early 1930s, the British physicist Robert Watson Watt was working on devices for tracking thunderstorms. He had developed a system of plotting their locations using oscilloscopes. So when in 1935, Watt suggested that he could use similar principles to track aircraft, the British government jumped at it.
Radar uses the same sort of approach that a bat uses to navigate in the dark. If you can send out some form of energy in waves, then some of those waves will bounce off, and some of them will be reflected directly back to you. And so if you can set up a system of emission and receivers that can detect those bounced radar waves, then you can pinpoint objects that you perhaps would not normally see visually.
Within weeks of Watt's claim, a test was conducted employing a BBC radio tower as the signal transmitter. Using an oscilloscope, changes in voltage bouncing back from a test aircraft emerged as a blip on a screen. And when the time delay of the signal was plotted against a calibrated scale, it pinpointed the aircraft's location. They had successfully tested radar. But the range at which the aircraft was detected was short due to the lack of transmission power and the relatively low signal frequency. Watt and his team decided that to be effective, the system had to emit waves at a very high frequency. By pushing the capacities of existing technologies, they continuously upped the range until by 1938, a working system of stations that could detect aircraft at 160 kilometers was built along the English East Coast.
The British successfully developed radar assets along the coast of the United Kingdom of Great Britain, guarding against the bomber fleets that the Luftwaffe were sending at them during the Battle of Britain.
Not that the whole process was automatic, far from it. In our admiration for radar, don't let's forget the men and women in the plotting center, for instance.
At the outbreak of hostilities, Chainholm, as it was called, consisted of just 21 stations. By war's end, there were over 100, all capable of detecting a target threat at distances of over 250 kilometers. It was the world's first early warning radar network to achieve operation.
Radar picks up all planes, but it enables you to distinguish enemy aircraft by the constant, unvarying pattern. Allied planes are equipped with apparatus that varies the oscillation.
In 1939, the British invented another device, the cavity magnetron oscillator, and its compactness was a game changer.
So subsequent to the Second World War, advances in electronics allowed radar hardware to be reduced in size and volume enough to actually put them onto aircraft. And so to this day, we continue to see radars located in the noses of combat aircraft.
Radar rapidly became an all-purpose device. One plane could spot every ship in an enemy fleet or convoy. The magic eye misses nothing.
Over 12,000 German bombers were intercepted and destroyed during World War II. Many of them with payloads that, had they been delivered, would have decimated Britain and her allies. Radar prevented that, and relatively unchanged, it has influenced every conflict since.
There's no such thing as dogfighting nowadays. I mean, you don't go Battle of Britain stuff anymore. Fighters don't see each other. Their radars see each other, but they don't.
Changing the very meaning of stealth, radar remains to this day one of the most powerful machines of war. After 2 world wars, the world slipped into a period of espionage, secrecy, and intrigue. A war in which stealth was the byword. It was the Cold War. The Cold War was a race between 2 nuclear-armed superpowers to secure political and ideological dominance. and it fueled a race for technological supremacy. But who was in the lead? Who had made the latest breakthrough? Out of this anxiety came the fastest non-rocket propelled aircraft ever built, the SR-71 Blackbird.
When the Cold War started, the U-2s were flying all over the world. During one of the missions, Francis Gary Powers, one of the U-2 pilots, was shot down. Three surface-to-air missiles fired at him. One of them came close and blew the aircraft up and blew him out of it. And so he ended up ejecting.
Powers' capture was a huge embarrassment for the United States. President Dwight D. Eisenhower reacted swiftly. He went straight to the top-secret Skunk Works division of Lockheed Martin and placed an order. He wanted a reconnaissance aircraft that could fly higher than a U-2, fly faster than a missile, and he wanted it tomorrow. It seemed impossible.
Building an aircraft that was going to fly faster and higher than the U-2 had never even been contemplated before. No aircraft had ever flown that high. No aircraft had ever flown faster than a missile. And they were given finally 20 months to build such an aircraft.
20 months to create an aircraft that could outrun a missile meant building an airplane that could travel at over 4,200 kilometers per hour, at altitudes beyond human tolerances. Immediately, the designers knew it couldn't be built from traditional metals. It needed to be fashioned from titanium. But America had limited supplies of rutile, the rare sandy soil from which titanium is extracted. The world's largest producer, ironically, was Russia.
Which caused a bit of a problem because the Russians weren't really excited about providing titanium to the United States. So what they did was go to off-site companies, offshore companies, and they went and bought the titanium from Russia.
Initial trials found that the heat generated meant the entire aircraft expanded at speed. The expansion would have caused a smooth skin to split or curl.
So they decided that they would have to build the airplane with the ability to actually grow in flight. And so the aircraft was built to actually grow 15 inches in flight from takeoff.
Then there was the question of altitude. The Blackbird was designed to reach altitudes into the stratosphere, but at 24,500 meters, nitrogen in the blood would make the skin boil. To combat this, pilots had to breathe pure oxygen for an hour prior to a flight to expel nitrogen from their blood. While the SR-71 was designed to rely largely on altitude and speed to avoid detection, it did have significant stealth capability. The underside of the fuselage was drawn out like a small boat, which limited radar cross-section. Special radar-absorbing alloys were incorporated in sawtooth sections on the aircraft's skin, and the wings and tail fins were tilted inwards, reducing direct radar reflection.
We did have defensive systems, but again, our defensive system primarily was speed. Faster you go, and the higher you go. That was how we got away from things.
The first operational Blackbird flight was in December 1964. When it flew, it became, and it remains, the fastest jet-powered aircraft ever made, with the capability of achieving a staggering top speed of over 3,500 kilometers per hour.
Its top speed's well over Mach 3.2. The SR is the only manned airplane that's ever done that. But Mach 3 was a different world. You can't imagine how quick you can get lost at that speed if something fails. You can get really lost really quick.
32 were built, none were shot down. It was only because of the development of satellite surveillance technology and high operational costs that the SR-71 was eventually retired in 1998.
It was a cost issue. Flying the SR-71 was not cheap. You know, every estimate I've ever heard was $1 million a flight. Whether or not it really was, I don't know. But that's a lot of money.
But the lessons learned from its design proved invaluable in developing the next generation of stealth aircraft. And that aircraft was the F-117 Nighthawk. It looks like it shouldn't fly, and it deserves its nickname, the Wobblin' Goblin. But though it may be ugly, the F-117 is another cutting-edge design by two names that recur in relation to stealth aircraft: Skunk Works and Kelly Johnson. Johnson led the design of the SR-71, and the Nighthawk was one of his last projects, born after combat experience in Vietnam, where increasingly sophisticated surface-to-air missiles repeatedly downed U.S. heavy bombers.
I mean, in Vietnam, I think the tally was up to over 800 missiles fired at the SR.
The most striking thing about the Nighthawk is its faceted design, which incorporates the most sophisticated stealth thinking of its time. This meant that despite it being the same size as an F-15, it appears on radar screens the size of an average bird.
One of the main reflectors of radar is actually the fan face, and so modern stealth designs try and hide that fan face from direct view. The F-117 did this in an interesting way.
The designers at Skunk Works set the engines deep within the airframe. The inlet screened with rotatable louvers to deflect any radar signal. The Skunk Works team also added noise minimization to counter the whine that jet engines produce, making the Nighthawk unnervingly quiet.
The F-117 Nighthawk was the first production truly stealth design that had been optimized from the beginning for reduced observability, principally again in radar cross-section, but also in infrared signature.
The result is an aircraft that is quiet, all but invisible, and extremely lethal. During the early morning hours of January 17, 1991, in response to Saddam Hussein's invasion of Kuwait, a fleet of Nighthawks slipped over Baghdad unseen by Iraqi radar and neutralized 37 targets. Over the ensuing weeks, they would strike with remarkable accuracy. Less than 3% of the American aircraft in Iraq were Nighthawks, yet they accounted for 40% of all strategic targets hit. And of the 64 made, only one was ever lost in combat. But while the F-117 was deadly, it carried a limited payload of just 2 laser-guided bombs of up to 900 kilograms each. The next challenge for aircraft designers was to create a strategic weapons platform that combined stealth with massive firepower. An assessment published by the U.S. Air Force concluded that 2 of these aircraft, armed with precision weaponry, could do the job of 75 conventional aircraft. It's the B-2 Spirit, the latest generation of stealth aircraft. With a wingspan of 52 meters, the B-2 is big. And yet, when a former head of the U.S. Air Force was asked the size of its radar signature, he described it as insect category. Conceived during the Cold War to infiltrate the Soviet air defense network and attack targets with nuclear weapons, the B-2 Spirit is a high-lift, low-drag, flying wing design. Engineers have long known that flying wings have minimal radar signature. They surmised that properly shaped and constructed using advanced composite materials, they could create the ultimate penetration bomber, undetectable by radar. So almost 80% of the B-2 is constructed out of a woven carbon graphite composite. With the aid of modern supercomputers, the outer skin was shaped to deflect radar energy in a way that is far more subtle than the Nighthawk. and a new alternate high-frequency radar-absorbent coating is applied to each B-2. Its 4 turbofan engines are internally mounted and have an exhaust temperature control system to minimize thermal signature. And its weapons capability is up to a devastating 18,000 kilograms in a single payload that can include a mix of weapons, allowing it to engage up to 4 different target types on any mission. It can also carry air-to-surface missiles with ranges up to 370 kilometers, allowing it to stand off an attack from well outside a conflict zone. Capable of attack missions from altitudes above 15,000 meters, with a range of more than 11,000 kilometers unrefueled and over 18,000 kilometers with a single refueling, the Spirit has the ability to fly to any point on the globe and engage a target without ever being seen. While stealth technology is essential to modern aerial combat, on the ground, different tactics are needed. During covert operations, to take out a target from a distance requires a weapon that is both silent and deadly. Up until the end of the 19th century, armies marched into battle with soldiers in orderly lines, wearing brightly clad uniforms to aid identification. But when a small bore force, either concealed in the landscape or using skirmishing techniques, very nearly defeated the mighty British Empire in South Africa, it ushered in a new way of fighting. We know it as guerrilla warfare, a tactic that values stealth over strength. In 1898, at the Battle of San Juan Hill in Cuba, 750 Spanish regulars delayed the advance of 15,000 US troops. The Americans were armed with single-shot rifles. The Spanish were using the same rifle as the Boer in South Africa, the Mauser 93.
The first major war that the US Army had fought since the American Civil War was the Spanish-American War of 1898. In that campaign, the Americans realised that their existing rifle was obsolete and they needed to come up with a new design.
The Americans paid $200,000 to license the design from Mauser and modified it at the US Armory in Springfield. They installed adjustable iron sights at the front and rear to assist accuracy at range and reduced its barrel length by 300 millimeters, creating a hybrid long gun that could serve as both a service rifle and a carbine, making it easier to handle. And so the M1903 Springfield was born. The Springfield has a muzzle velocity above 850 meters per second, over 250 meters per second faster than its predecessor, meaning its effective range was doubled to almost 550 meters. And absolute range was increased to well over 3,000 meters. This vastly improved range of the Springfield was in part due to the decreased aerodynamic drag of the French Spitzer round, which replaced the standard bullet's rounded nose with a pointed tip. And it was smooth and reliable under the worst battlefield conditions.
The Springfield rifle was a robust design. New recruits in that vastly expanding army which the Americans created in the First World War in 1917 found it relatively easy to train and become competent in the weapon.
10 to 15 shots a minute was easily achievable, with the shooter able to fire from a safer range using smokeless powder, making them far more difficult to detect. Over 3 million were produced.
The Springfield rifle was renowned for its reliability in combat, and it was such a sound design that a sniper variant of the rifle continued to be used during the Second World War, more than 40 years after the original design was conceived.
In the hands of an expert marksman, it could reliably take out a target at over 1.5 kilometers. Add an optical sight, and what you had was a potent specialist weapon. And they gave a name to the men who operated such weapons: They called them snipers. When Germans on the Western Front began consistently claiming lives, firing across seemingly impossible distances, the Allies initially assumed it was pot luck. It wasn't until they began moving through German positions and stumbled upon rifles equipped with telescopic sights that they understood what had been happening.
Really, the story of the sniper and the sniper rifle begins in earnest in the First World War, when each of the participant nations realized they needed a much more precise version of their infantry rifle, their standard, usually bolt-action infantry rifle. And that's really what these early sniper rifles were.
The British wasted no time in emulating the German tactic, and they elevated it to a new level. They established training camps where British snipers honed their shooting skills and learned to gain advantageous positions using improvised camouflage known as ghillie suits. The underside of the ghillie suit is reinforced with heavy canvas to help pad a sniper's torso during hours or days of lying on his stomach. Camouflage netting is attached. To this is added shredded hessian and other frayed materials, as well as elements of local vegetation. Early snipers often acted alone. Many used iron sights, but optics helped realize a rifle's potential.
It meant that you didn't have to line up mechanically your front and your rear sight with your eye with the target. You just have to put the crosshairs on the target. Makes it sound simple. It's not.
But as sniping became more effective, so too did countermeasures.
We can see the classic contest between offense and defense beginning to take place. We have snipers who are highly trained, and we have the opposition, in this case the Germans, developing armor to protect themselves.
The increasingly mechanized battlefields of World War II dramatically changed military tactics on the ground. And naturally, armies across the world began to look at the potential for specialist snipers to inflict damage on more than just men.
But how on earth does the individual infantryman harness physics in a portable weapon to perhaps kill a tank? It's an extremely difficult thing to pull off, and different answers were arrived at.
Early anti-tank, or anti-material weapons as they became known, were extremely cumbersome. More mobile than an artillery piece, but only just. The British boys' anti-tank rifle of World War II was over 1.5 meters long, weighed almost 20 kilograms, and required a crew of 2 to operate.
And their story kind of peters out as tank armor just gets too thick to defeat reliably. And there's a point in the Second World War where the anti-tank rifle becomes absolutely useless, essentially.
But tanks were not the only armored vehicle on the battlefield. A weapon was still needed that could stop lighter armor. And to make that weapon difficult to detect meant reducing its weight, suppressing its noise, and taming the incredible recoil forces it would generate. In the 1980s, a weapon arrived that filled all those criteria: the Barrett M82. The Barrett M82 sniper rifle is the benchmark large-caliber anti-material rifle that revolutionized the field of military sniping. Referred to as a multi-role weapon system, the M82 has an effective range of over 1,800 meters. But anti-personnel work is not the weapon's primary purpose. It is more commonly deployed against hard targets, like buildings, armored vehicles, parked aircraft, and communication systems. To create a weapon of this power and portability first required a reduction in weight.
There's a constant quest to lighten all weapons, but especially weapons that tend to be very heavy and cumbersome, simply because you can use them much more flexibly.
To achieve this, the Barrett's barrel is fluted, a design that also improves heat dissipation. Elements of the stock are constructed using lightweight plastics. But what's truly unique about the Barrett is its buffer system. The entire barrel is set on rails and travels back 3.8 centimeters against springs, a revolutionary development that allows it to be fired from the shoulder, unaided by tripod bracing.
The Barrett's recoil-operated system sacrifices a little accuracy for low recoil, which is very important when firing an extremely powerful cartridge like the 50 Browning machine gun cartridge.
All of this allows the M82 to deliver previously unheard of levels of energy and distance with low observability. A sniper rifle capable of putting a 50 caliber round through the block of a truck engine from over a kilometer away. But the effectiveness of a modern sniper is enhanced not just by the rifles they use. Advances in glass manufacture have led to massive increases in standard magnification, and the increasing use of transparent polymers has greatly improved the light transmission of modern scopes. Such scopes, fitted to rifles like the M110 sniper system, equip the sniper with what is a true precision weapon. With the M110, that precision begins with the barrel.
If you think about the microscopic imperfections in a rifle barrel, every one of those can upset the bullet very, very slightly. And so if you're able to go down to that microscopic level, and if you're able to remove all of those imperfections, in theory, you will have an ultra-precise bore, something that they couldn't have dreamed of in 1918.
The M110's 50-centimeter chrome-plated barrel is made from the highest quality modern steel with greatly reduced imperfections. It also features what is called 5R rifling.
The important thing with sniper rifles is that you minimize barrel vibration when you fire the projectile, and that is so important for accuracy, because as you fire the projectile, the barrel may have a tendency to vibrate. And if you minimize that amount of vibration, then that's going to improve the level of accuracy.
5R rifling reduces projectile damage, ensuring the projectile remains more uniform. And a more uniform projectile translates into less vibration and improved accuracy. The changing nature of battle revealed the limited engagement capabilities of traditional single-shot bolt-action rifles. This was particularly problematic in urban Iraq during the US-led invasion, where non-repeating sniper rifles became a tactical liability. With a larger 20-round magazine, a sniper carrying an M110 who finds themselves under threat can easily switch the weapon into automatic mode, allowing them to fight their way through to safety. 2 weapons in one, and yet extremely accurate. In the hands of a skilled sniper, the M110 can group 10 shots fired rapidly over a distance of more than 90 meters within a radius of less than 1.5 centimeters. Stealth on land relies on silence, camouflage, and guile. But in the wide expanse of the open ocean, it's much more difficult to hide. At sea, the stealthiest place from which you can do damage to enemy shipping is not from the surface, but below it. On the morning of the 5th of September, 1914, HMS Pathfinder, the lead ship of the British Pathfinder class of cruisers, was spotted by the German U-boat U-21. Stalking her at periscope depth, U-21 fired a single 50-centimeter torpedo at a range of 600 meters. Within minutes, she was lost. It was the first sinking by a U-boat in World War I. Thousands more were to follow.
Many naval people in the beginning of the 20th century regarded the submarine as a really underhanded weapon, a weapon to be used by the coward. Yet the ability to approach unseen and to wreak damage revolutionized warfare at sea.
The undersea boat, or the U-boat as they became known, was more a submersible ship than a submarine as we think of them today.
They were fast on the surface. They could do something like 17 knots, but dived only about 7. So they would do most of their hunting on the surface and then dive for the attack.
There were many Allied submarines, but what made the U-boat superior and gave it its tactical edge was its diesel-electric propulsion system. The Germans had long understood the value of diesel engines and led the world in their design. In 1915, a reliable 4-stroke diesel engine was produced that far outstripped the performance of any Allied equivalent. The U-boat could keep pace with most merchant ships of the day, with a range that allowed them to choose their time to attack. Using electric motors to get them within range, they would surface and either engage with deck-mounted guns or torpedoes. U-boats quickly became the most prolific killers on the seas. While in 1914, German surface ships sank 55 ships, compared to only 3 by U-boats, the following year, this was reversed, with U-boats sinking 396 Allied ships, compared to only 23 by surface craft. Between 1914 and 1918, nearly 10,000 ships, thousands of planes and dirigibles, and more than 100,000 mines were deployed to combat a U-boat fleet which totaled just 340 submarines. The Allies may have eventually won the war on land, but the success of the U-boat campaign underscored how important and devastating submarine warfare could be, a lesson that was repeated to an almost decisive effect in the Second World War. The Type 7 U-boat was the workhorse of the German submarine fleet during World War II.
They were designed really for service in the North Sea and in the western approaches to Europe. They were very effective in their job of trying to cut off sea communications to Britain. And there were more Type 7 U-boats built than of any other submarine ever.
Over 700, in fact. But the Type 7 was more an evolution rather than a revolution.
They were quite a small submarine, and in terms of their technology, they were little changed from the submarines of World War I, with similar size and similar capability.
Additions included large external tanks holding 33 tons of extra fuel, which increased range, and supercharged diesel engines gave a slight increase in overall speed. Improvements in the efficiency of the electric motors extended the time they could remain submerged, and they carried an increased load of torpedoes. But it was improvements in shipboard communications that was their deadliest asset. It allowed German submarines to hunt in groups that became known as wolf packs.
Well, wolf pack was a group of submarines operating together. They could be very, very effective because they could surround a convoy and attack it from multiple directions all at once.
Undoubtedly, one of the most formidable assets of the Axis powers in the present phase of the war is the U-boat.
Initially, they were very effective in disrupting supplies to Britain. In the first 6 months of the Second World War, Britain lost more than 300 ships, while the Germans lost just 17 submarines. And as the war spread, with America's entry, so too did the Battle of the Atlantic.
The U-boat campaign, certain to be intensified, is Hitler's greatest hope of staving off defeat. He has hundreds of U-boats at sea now. He'll undoubtedly have more. The answer is to destroy them.
But luck began to run out. as submarine countermeasures evolved.
Allied air patrols over the North Atlantic became more effective, and radar became more available, which made them very vulnerable. If you want to combat an air attack on a submarine, you have to stay well submerged and keep out of the way. And that was difficult because, like many early submarines, the Type 7s were basically a surface ship which could dive.
The Germans realized they needed a way to carry out such operations while remaining submerged. And the answer to that was the snorkel.
The Germans adopted the Dutch snorkel and retrofitted it to quite a number of the Type 7 submarines, which made them much less vulnerable.
Although the snorkel improved the odds, improvements in detection technology, combined with the development of specialist ships to hunt and destroy U-boats, meant that they were no longer the supreme stealth weapon they had been. In fact, by 1945, U-boat losses were routinely 30 per month, and in April of that year, they exceeded 50.
Not so long ago, the Battle of the Atlantic was the most critical factor in the war. Now, convoy after convoy, all strongly escorted, crosses the Western Ocean virtually unmolested in comparison with those days of crisis. When U-boats appear, it's they who are hunted now.
But the end of the war and the birth of the nuclear age unlocked a power source that would redefine submarines and restore their place as perhaps the most feared of all stealth weapons on the planet.
After World War II, the British put most of their effort into commercial nuclear development. But in 1947, Westinghouse were authorized by the US government to develop a nuclear reactor which was capable of being fitted into a submarine.
That reactor was fitted to a submarine named the USS Nautilus, and it was revolutionary. Launched in 1955, the Nautilus was able to achieve a submerged speed of 23 knots, and her hull could withstand pressures at depths over 200 meters.
The important thing about the nuclear submarine is it can remain submerged, really, for a very long period of time. And the submarine's endurance is really determined not by the fuel or the battery capacity, but by the amount of food you can carry and the endurance of the crew. And that was a major revolution in submarine design.
From 1955 to 1957, the Nautilus was put through a series of trials. Trials which showed her revolutionary teardrop-shaped hull would allow her to match speed with those on the surface. No longer would the submarine be a fast surface ship that temporarily submerged, but a fast submersible ship.
I think the most important thing about Nautilus is that she proved the value of nuclear power in submarines. By the mid-1950s, the United States had stopped building conventional diesel-electric submarines.
To prove the supremacy of nuclear power, on the 1st of August 1958, the Nautilus submerged near Alaska and surfaced 96 hours later northeast of Greenland, having completed the first submerged voyage under the North Pole.
But all went without a hitch. Nautilus passed safely on her route right under the pole. A tremendous achievement and a moment of relief, I should think, for all on board when she surfaced.
The Nautilus had demonstrated that she was at the cutting edge of stealth technology. But during the Cold War, as the Soviets developed their own nuclear submarines, the US was compelled to stay ahead. "62 Los Angeles-class submarines, the largest group of vessels constructed for the United States Navy during the Cold War, were specifically designed to counter the Soviet submarines that the Americans believed would, in the event of hostilities, target the heart of their Navy, the carrier groups. Much of the information about the Los Angeles class is classified. We know that it is capable of 20 knots on the surface, and its reported top speed while submerged is 33 knots. If continuously operated, its propulsion plant requires refueling just once every 9 years. The Los Angeles-class submarines are armed with a mix of both land attack and anti-ship versions of the Tomahawk missile, complemented by 25 torpedo tube-launched missiles, including the Harpoon anti-ship missile.
Submarines, of course, are a pressure vessel. They consist of several major components. The most principal one, of course, is the pressure hull. And the more cylindrical that is, the better it withstands pressure.
The deeper you go, the more difficult you are to detect. And depth means pressure. Increased power from nuclear reactors allows submarine hulls to be thicker. But a hull's strength is also measured by how elastic it can be under pressure. And this yield strength requires special steel alloys. Although the operating depths of submarines are secret, their crush depth can be calculated if you know what they're made from. The Los Angeles class have pressure hulls made with HY80, a nickel chrome alloy with incredible strength and elasticity. This puts their crush depth somewhere around 600 meters. Deep and stealthy. But stealth at sea is no longer the sole domain of the submarine. At almost 183 meters, the largest destroyer ever commissioned for the U.S. Navy, the Zumwalt-class guided missile destroyer, is as close as any ship has come to being invisible.
They're big ships. They're something like 15,000 tons, so to call them a destroyer is something of a misnomer. But it's a very stealthy ship, which was difficult to find with radar.
To make a ship of this size difficult to detect has required a complete shift in naval design thinking and the application of lessons learned from aviation stealth technology, beginning with the shape.
The structure is designed with a lot of tumble home so that the upper deck is narrower than at the waterline.
The opposite to that of traditional vessels, resulting in a significant reduction in its radar cross-section. Like the F-22, the weapon systems are discrete. The decks are clear with virtually no sharp lines that could return a radar signal to its source. On a typical warship, you see an arrangement of spinning dishes and antennas sitting atop a high-profile mast. The Zumwalt's deckhouse is a clean, angled structure, straight out of the F-117 design book. Its array of radar sensors and communications hardware is integrated directly into the deckhouse skin, which is built of composites, much like the B-2. By incorporating these lessons, designers have managed to give the Zumwalt an almost 15,000-ton heavily armed warship capable of 36 knots, a radar cross-section the size of a fishing boat. Improvements in stealth design are continually being counterbalanced by the ongoing development of detection methods. The Zumwalt represents another beginning in the race to appear invisible. And science continues to push the boundaries of what seems possible. Current studies involve cloaking aircraft in plasma shields, fields of ionized gases that absorb all radar signals, and experiments with technologies that bend light waves to render objects, or even people, invisible to the naked eye. It seems that if science fiction can think of it, militaries will try to make it a reality. From concrete bunkers to vast underground railways, machine guns capable of firing thousands of rounds a minute, to precision lasers able to instantly neutralize a threat, intercept fighters to armor plating, the machinery of war with the ability to attack, are almost worthless without the machines that protect. Without defense, there would be no battle, only surrender. This is the story of defense. When flimsy aircraft first appeared above the battlefields of World War I, few could have imagined the influence they would have on the shape of war. In less than 20 years, they went from curiosities to weapons of incredible destructive force. World War II had initiated a new chapter in aerial warfare. And to combat that threat, nations on both sides looked to ways to defend their airspace, in the air and from the ground. Amongst the German arsenal of anti-aircraft weapons were a variety of small-caliber light artillery pieces for low-level attacks. For aircraft operating at higher altitudes, it had developed a weapon that became simply known as the 88. A supreme anti-aircraft gun that had two aims.
The first was to keep the bombers high, rather than letting the bombers come lower and be more accurate. And the second was to kill bombers. There were belts of 88s, both on the approaches to major German cities, but also along the coast, so that the Allied bombers had to cross literally bands of heavy and accurate anti-aircraft fire to approach the cities of the Reich to bomb them.
The secret of the 88's power lay first of all in its caliber. At 88 millimeters, it was a very large exploding shell fired with a timer that meant it would detonate at a set altitude. But it also had a very long barrel, which gave it a very high muzzle velocity, and with it, the ability to fire a shell to an altitude of more than 7,500 meters, well within the target range for most bombers. But what really set the 88 apart was its rate of fire.
So instead of having to load the shell and sight the gun each time, the Krupp automatic loading meant that it could fire 15 to 20 shots a minute, which meant that you could literally put up a barrage. So a battery of 4 guns could put up 80 shells in the course of a minute, which is a wall of steel which the aircraft have to fly through. It's the technical capacity of the German armaments engineers in the 1930s that are actually defending the Reich into the 1940s.
Over 20,000 German 88s were produced, including variants and modifications derived from lessons learned in action.
The German 88mm gun is one of the most extraordinary artillery weapons of all time. Every nation developed a heavy anti-aircraft weapon, and none of them were as good as the 88. And the British and the Americans never had a gun to match the 88's capacities.
While the 88 may have been a supreme weapon in its time, the development of attacking machines waits for no weapon. The character of war at sea has produced new threats that demand ever more sophisticated means of protection. On the 2nd of April 1982, Argentine forces mounted amphibious landings off the British colony of the Falkland Islands. The British and the Argentine forces squared off in what was essentially a war at sea. What became immediately obvious to both sides was that in maritime warfare, things had changed. And the key to that change was the introduction of the anti-ship missile.
Ships were incredibly vulnerable to these systems. If you couldn't shoot down the aircraft or you couldn't take out the host ship before the anti-ship missile was launched, you were in a sense helpless.
While militaries around the world had known of the dangers of anti-ship missiles, the loss of 6 British warships during the Falklands conflict offered the first real-world example of their potential destructiveness. What was needed to combat that threat was a last-ditch defense system. And for a last-ditch defense, you need something that's incredibly fast and responsive. A system capable of destroying an inbound missile in flight on the last line. The Phalanx Sea-Whiz is such a weapon. The Phalanx is an automated close-in weapon system built around the Vulcan 6-barrel Gatling autocannon. In use since the late 1950s on U.S. attack aircraft, the Vulcan fires heavy 20mm shells at the astonishing rate of 4,500 rounds per minute. Housed in an entirely self-contained turreted mounting, the gun is linked to an automated radar fire control system that enables it to automatically seek, detect, track, and engage incoming targets. A task it can perform entirely autonomously.
It doesn't require a human in the loop. It will simply pick up the target, fire at it, and destroy it. And because it has this enormous rate of fire, it's effective against things like incoming anti-ship missiles, but even large artillery shells.
The advantages of an autonomous system are many, but the most significant is in targeting and response times.
Taking a human out of the loop means it can react much quicker than a human being could, and it is very, very effective. It doesn't get worried, it doesn't get concerned, it doesn't get tired. If the systems work as we hope that they will someday work, it is potentially more discriminate and more proportional than a human being.
Where the Phalanx's autocannon effectively shreds the inbound projectile, the integration of the Phalanx's control system with a commercial-grade laser could lead to a different future for air defense weaponry. To the untrained eye, it looks like a telescope, and the operators sitting behind a screen look as though they're playing a video game. But this is no game. Lasers are at last entering military service, and warfare will never be the same. It is the laser weapon system, or LAWS.
The first idea of lasers came from Einstein in 1913. Einstein predicted that we could generate light not with multiple frequencies like in a lamp, but with a single frequency, and we could order light so it could go in the same direction.
In theory, laser weapons target an object with a train of brief pulses of high-intensity light energy. The heat generated causes rapid evaporation and expansion of the surface, creating shock waves that damage the object. It's taken over 50 years to make them practical battlefield weapons, overcoming numerous technological hurdles along the way, the biggest being the conversion of energy into the actual beam emitted. Early lasers could only convert 10% of the total power input into light energy, which meant that to create an effective laser weapon, a huge power source was required. Using the latest technology in optics, LAWS projects an infrared beam from a solid-state array that converts 50% of available energy. And when its beam is tuned to high output, it can affect the structural integrity of aircraft, burn holes in the hulls of small boats, heat artillery shells in midair, causing them to explode, or heat storage containers at a fuel dump until the fuel ignites. And tests aboard the USS Ponce in 2014 have proved it works. Among the advantages of a laser, compared to a projectile weapon, is that it requires no projectile. There is no need to manufacture, transport, or store munitions. It is solely reliant on a power source, which makes each shot virtually cost-free.
It's much cheaper than a missile, for example. If you fire a missile, it may cost $100,000 or $1 million. And with a laser shot, it can cost like $2 or $1.
Lasers may never totally replace other weapons. An international agreement means they can't be used to target individual people. Still, for targeting practically everything else, the time of lasers is finally coming. It's warfare at the speed of light.
We may well see near-future wars in which autonomous robot drone swarms are attacking a target and being shot down by lasers. It sounds like science fiction, but it's really happening.
Fighter aircraft have always captured the public attention. In World War I, dogfights between biplanes sought to control the skies so that just one side could see the battlefield to direct their artillery. But in World War II, as the skies of Europe and Asia filled with bombers targeting cities, they took on a much more serious role. Anti-aircraft weapons can only do so much in defense of those on the ground. And sometimes, the only way to defend is to take the fight to the skies. On the 16th of July, 1940, Adolf Hitler ordered the preparation of Operation Sea Lion, a potential airborne and amphibious assault on Britain that would come once the Luftwaffe had established air superiority over the UK. And so the famous Battle of Britain began. And standing between the Luftwaffe and victory were two aircraft, one of which was Britain's first monoplane fighter, the Hawker Hurricane, an aircraft designed in the mid-1930s.
At the time, the whole RAF was still flying biplanes. Around that time, the Messerschmitt 109 came into being. Single-engine, stress-skin monoplane fighter, heavily armed, quite fast, and the RAF said, well, we don't have anything to match it. So they put forward a request to British industry, and the Hawker Hurricane and the Supermarine Spitfire were the initial results of that.
The Hawker Hurricane was in many ways a transitional aircraft, constructed using a mix of old and new techniques. A steel tube fuselage was bolted together, over which were fitted wooden stringers that gave the aircraft its streamlined shape. The wing structure was forged of aluminium, but unlike the Me-109, which had a modern aluminium stress skin, the Hurricane was covered in fabric. And that fabric skin would prove to be one of the Hurricane's strengths.
The Hurricane was easier to turn around than a Spitfire, particularly battle damage, because more often than not, you just throw a fabric patch over a bullet hole and send it out again.
While the Hurricane was an impressive fighter, it could not have won the Battle of Britain alone. The German Messerschmitt 109 was simply too fast. Hurricanes, supreme against incoming bombers, needed to fight alongside an aircraft that could match the capabilities of their Messerschmitt escort. That aircraft is perhaps the best remembered fighter of World War II, the Supermarine Spitfire. Where the Hurricane had been something of a compromise between old and new, the Spitfire heralded an all-new method of building fighter aircraft. It was an all-metal design with a monocoque frame and aluminium alloy stress skin covering the outer surfaces, making the Spitfire incredibly light and streamlined, contributing to its legendary maneuverability. It also made it difficult at first to build with the industry required to manufacture and work metal airframes, and the particular manufacturing issues surrounding the famous elliptical wing, a complicated design intended to reduce drag and increase aerodynamic performance. That wing proved revolutionary, and along with the Rolls-Royce engines, it gave the Spitfire astounding aerodynamic capability, and perhaps more importantly, speed.
The role of the Spitfire was to take on the fighters. When the Germans sent across their Heinkel 111s and Junkers 88s, they were escorted by Messerschmitt 109s and 110s. It was the Spitfire's job to take on those two aircraft to allow the Hurricanes in to take out the bombers.
Technically, it had a slight edge on the Messerschmitt, but the contest was close run and often came down to the skill of opposing pilots. The Spitfire may be better remembered than the Hurricane. The two aircraft worked very much together.
Without the Hurricane backing up the Spitfires, and the Spitfires looking out for the Hurricanes, the Battle of Britain would have ended very differently.
When the Spitfire and the Messerschmitt did battle in the skies above Britain, they were among the fastest aircraft of their time. But as the war came to a close, jet engines began to roar. And within less than 5 years, in the skies over Korea, a new jet aircraft dominated, the technologically advanced MiG-15. Developed in 1947 to intercept bombers, the MiG-15 design drew on valuable lessons learned from World War II. The first thing acknowledged was that it had to be fast enough to intercept targets before they could enter friendly airspace. To achieve this, the Russians copied and improved on British Rolls-Royce jet engines sold to them at the end of the war. The power of the new jet technology was then combined with a new wing design to give it unrivaled speed.
Swept wings allow for a similar lift capability but less drag. Instead of trying to push a plank through the air horizontally, if you sweep it, it's easier to move through the air.
This combination of two new ideas made for astounding performance gains over earlier aircraft. The MiG streaked through the sky at close to 1,100 kilometers per hour. Its rate of climb was 3,000 meters per minute, almost twice as fast as the first-generation straight-wing jet fighters like the Gloucester Meteors that were sent to combat. And where the MiG also shone was in armament.
Fortunately, the plane was delivered to the Air Force combat loaded, so armament tests could be made.
The Russians had learned during World War II that aircraft equipped with machine guns simply couldn't inflict sufficient damage to cripple large aircraft. And so the MiG-15s were equipped with one 1.45-inch and two 9-inch cannons. As a result, when MiG-15s began mauling B-29 superfortresses, the effect was as startling to the Americans as it was devastating. The U.S., which until the MiG's introduction had been able to bomb with impunity, was forced to abandon daylight raids since their bomber escorts, straight-winged F-80 and F-84 fighters, were completely outclassed. With UN air superiority on the brink of collapse and the Korean Peninsula at risk, the United States deployed the only aircraft which could hope to stop the MiG, the untried F-86 Sabre. The MiG-15, though incredibly capable, was a jet aircraft that had been built in a similar way to aircraft from World War II. Still very much a mechanical airplane, in that all of the control surfaces were operated by wires and pulleys connected to the flight stick. The F-86 Sabre, by contrast, was an all-new aircraft design that attempted to apply the very latest developments in aerodynamics, avionics, and jet engine technology in a single package.
It's the first American aeroplane to have full powered flight controls. So the ailerons and elevators are controlled hydraulically via electrical signals and multitude of valves and switches, and it's a very complicated system but very advanced for its time. The main role of the Sabre was to combat the MiG-15s, and they were fairly evenly matched depending on the altitude that the fight took place. At lower altitudes, the MiG was more capable. It was a more aerobatic aeroplane at low altitude.
Despite the Sabre's disadvantage at low altitude, the two aircraft proved to be fairly evenly matched in performance. The Sabre was slightly quicker, and although it couldn't fly as high or climb quite as quickly as its Soviet-made opponent, it could dive faster, was more aerodynamically stable, and importantly, it was fitted with the latest radar targeting system that automatically acquired enemy aircraft during high-speed dogfights. A total of 224 Sabres were lost, of which about 100 were the result of aerial combat. But they destroyed 566 MiGs, although the disparity between the two was lessened when the MiG was in the hands of an experienced Russian pilot. Regardless, and despite looking outwardly similar, it was the technologically superior Sabres which won the day. And just as agile aircraft are built to attack and defend bombers in the sky, on the sea, fast, high-powered vessels defend convoys and less mobile maritime assets. Although these heavily armed protectors aren't called fighters, they're called destroyers. At the beginning of the 20th century, navies across the world had developed a fascination with torpedoes, which were considered the most feared weapons in maritime warfare. Every navy in the world had a fleet of torpedo boats, and the bigger navies a corresponding fleet of small, fast torpedo boat destroyers. In World War I, the war at sea very quickly evolved in a way that hadn't been expected. German submarines armed with torpedoes posed a constant threat, and a need arose for fast, well-armed vessels to protect the fleet and merchant ships from the menace. Vessels that could operate in heavy seas. In 1916, the British commissioned a design for a much larger torpedo boat destroyer that could fill the role and lead the existing destroyer fleet. The result was the V and W class. The principal characteristic of the early destroyer was speed, and the V and W class were an evolution of those designs. Long at 95 meters and narrow with a beam of just 9 meters. Their compact hull design featured a higher freeboard than previous, which gave them much greater ability in heavy seas. And with a top speed of 34 knots, they were fast and heavily armed.
They introduced a number of features, not the least of which was the different arrangement of the guns. 2 guns forward, one superimposed above the other, and 2 guns aft, providing the familiar A and B and X and Y turret configuration, which proved to be very, very successful.
Built between 1916 and 1924, 67 of the ships were completed, many going on to serve in World War II.
It became a style pattern, so to speak, for British destroyer design for the best part of a quarter of a century.
But threats evolve, requiring defenses to do the same.
The World War I concept of a long line of destroyers steaming at 30 knots heading towards the enemy battle fleet with the torpedo tubes trained over the side to fire torpedoes and sink the battleships is long gone. That's 100 years ago. That's a different style of warfare.
In fact, the style of warfare has changed to the point where today there are no battleships and very few battle cruisers, as the most destructive ships of the naval line were once called. Today, that frontline role is undertaken by destroyers. And for the United States, since the late 1980s, that role has been fulfilled by one design: the Arleigh Burke class. Just like the destroyers of old, the Arleigh Burke are long at over 150 meters, narrow, have a shallow draft, and a top speed in excess of 30 knots. But that is where the similarities end.
It is a ship which, in many ways, is far more capable than a World War II cruiser. It is able to strike land targets at some distance. It can engage other ships. It can engage aircraft. It is able to control large areas of sea with modern fire control systems, and they're a powerful warship.
Ships like the Arleigh Burke class are referred to as multi-mission destroyers, taking on the role of both defender and attacker. With Tomahawk cruise missiles for attacks on land-based targets, Harpoon anti-ship missiles, acoustic homing torpedoes for anti-submarine duties, a suite of short, medium, and long-range missiles designed to intercept enemy ballistic missiles at any stage of their trajectory, and the latest surface-to-air weapons, the Arleigh Burke class is an incredibly capable weapons platform, with a level of firepower that crews of the V and W class destroyer would have found unimaginable. But the capacity to attack is nothing without the ability to defend. The Arleigh Burkes incorporate elements of stealth design in the angled hull and the tripod mainmast, which make them more difficult to detect by anti-ship missiles. This is combined with the latest air and missile defense systems that can detect a golf ball-sized target as far out as 166 kilometers, giving it ample time to engage countermeasures. Should something get through, a suite of close-in weapons, including the Phalanx Sea-Whiz, stand guard on deck. And an air filtration system makes the Arleigh Burkes the first U.S. warships designed to endure in the event of a nuclear, biological, or chemical war. If the Arleigh Burke class is the ultimate expression of the old adage, the best form of defense is attack, then land-based defensive structures would represent the directly opposing view, one that implies that the best form of defense is attrition. With the weaponry of the 20th century evolving at a rate that in many ways outpaced tactics, and with mechanization increasing the speed of battlefield advances in World War II, nations turned to the age-old strategy of permanent or temporary structures designed to slow an enemy and defend positions. Structures that in World War I had resulted in utter carnage. The last line of German defense in World War I was a 160-kilometer stretch of concrete bunkers and pillboxes in front of which stretched tracks of barbed wire that were at times 91 meters deep. It was called the Hindenburg Line. Under intense pressure, the Hindenburg Line had failed. But it had provided enough resistance to encourage the French, alarmed at the possibility of renewed German aggression, to build their own defensive wall in 1930. The Maginot Line.
Obviously, the French knew, especially from World War I, that you need a defensive position, a defensive posture. So the Maginot Line was a series of interconnecting pillboxes. You had tank ditches, you had physical obstacles in the way to try and deter somebody from coming through.
The Maginot Line was not a single continuous structure. Instead, it was composed of over 500 separate buildings, each arranged according to a detailed plan. The key units were 50 large forts, or ouvrages, which were located within 14 kilometers of each other, along the borders with Germany and Italy. These forts were often connected using reinforced underground tunnels and were placed near enough to each other to provide interlocking fields of fire. The surface areas of these vast bases were protected by steel-reinforced concrete, which was up to 3.5 meters thick. A depth capable of withstanding multiple direct hits from the largest artillery. They were fitted with steel turrets, domes that nestled on the ground when under attack, and elevated for firing. In theory, the Maginot Line was capable of creating a massive continuous line of fire that should have devastated any attack. However, it had one major failing. It was not mobile, and warfare had changed. Mobility had caught up with firepower. And when in May 1940, the German army attacked through Belgium, as it had in World War I, and crossed the supposedly impenetrable forests in the Ardennes, the closest the thousands of French soldiers manning the Maginot Line came to seeing action was watching unchallenged waves of German bombers flying over it. In 1942, there was only one way to attack Europe en masse, and that was by sea. And with Germany in almost total control of the continent, Hitler decided to keep it that way. With a workforce of close to 1 million, the Germans began construction on what would be the largest network of fortresses built in the 20th century, the Atlantic Wall. A formidable collection of an estimated 15,000 reinforced concrete bunkers, stretching across the Belgian and French coasts from the Norwegian to the Spanish border. The Atlantic Wall consumed more than 1 million tons of steel and 17 million cubic meters of concrete. In all, there were 70 batteries along the Danish coastline, with 293 large caliber guns, 225 batteries in Norway, with over 1,000, and 343 batteries along the French coast, which included 1,348 heavy weapons and an assortment of anti-tank and anti-aircraft positions, machine gun posts, munitions storage areas, and bunkers housing supplies and power generation equipment. The Atlantic Wall was the first line of Fortress Europa, as Hitler called it, and the 630-kilometer West Wall, or as it was better known, the Siegfried Line, the last. Built between 1938 and 1940, the Siegfried Line incorporated more than 18,000 bunkers, pillboxes, and tunnels, stretching along the French border from the Netherlands to Switzerland. Designed to slow an offensive while reserves are brought up, the Germans knew the speed of tanks posed the greatest threat, and so a vast network of tank traps were central to the line's design.
So generally you've got to have a trench that's wide enough to trap the tanks where they are so they can't break through. Then you've got tetrahedrons, so big concrete triangles, so tanks can't climb over them basically, because if they do, they get stuck on the point and lose traction.
And like the barbed wire of World War I that was often laid to funnel troops to their death, the tank traps were designed to lure tanks to their destruction. But defensive walls can be breached with enough concentrated manpower in one location. And once breached, they can't be moved. The Atlantic Wall was pierced when 156,000 Allied troops landed on the beaches at Normandy. And thousands of ships and aircraft threw their might into General Eisenhower's Great Crusade. It marked the beginning of the end of Fortress Europa. And like the barbed wire of World War I, the Hindenburg Line, and the Atlantic Wall before it, the Siegfried Line offered some respite to retreating German troops, but eventually buckled under the weight of the Allied advance. Like its predecessors, it fell victim to the mobility of modern warfare and was overrun in early 1945. And with it, the Third Reich fell. If the enduring image of the First World War is a misery of wire and mud, it was partly made so by a revolution in armaments. Trenches and barbed wire will slow in advance, but waves of men can only be completely stopped by firepower. Hiram Maxim was a man of great curiosity, an inventor of a diverse range of items. One of his creations would make him a wealthy man and change the course of history. The story goes that Maxim was talking with a friend in Europe who told him to forget his chemistry and electricity. If you want to make a pile of money, invent something that will enable these Europeans to cut each other's throats with greater facility. And then he had a chance experience.
So the story went that Maxim fired the M1903 Springfield rifle and was struck, literally, by the recoil. And it occurred to him that he could harness that power.
Maxim designed a system that took the force of the gun's recoil to operate it automatically by simply using the explosive energy from the firing of a projectile that would otherwise go into a rifleman's shoulder and have it drive the working parts backwards. Maxim conceived the idea of what we now know to be the machine gun.
Later, Maxim's company was bought by the Vickers Company, which was a major British armaments company. Vickers made some modifications to the design to make it more efficient, and in 1912 produced what we know as the Vickers machine gun.
What they produced was a weapon that could continuously fire an extraordinary 450 rounds per minute. But that rapid firing generated extreme levels of heat.
One of the really distinctive features of the Maxim series of guns, others as well, is the big blocky barrel section, if you like. Well, the barrel is actually very slim, and the barrel sits inside what is actually a water jacket.
The jacket around the main barrel contained 3.7 liters of water that had to be kept up to the weapon to ensure that it didn't overheat. In the stalemate that was the Western Front, it was the perfect defensive weapon.
Where you've got a fixed machine gun and you're able to dominate the landscape in front of you. The classic movie image of swinging back and forth this weapon that's utterly devastating. The Devil's Paintbrush is one of the nicknames for Maxim's gun later on.
The Vickers machine gun was such an efficient design, it remained in service in some fashion until the 1960s. But the need for a constant water supply meant it took as many as 6 men to operate it. With increasingly mobile attacking forces, unreinforced static defense placements quickly became tactically obsolete. Modern warfare demanded defensive mobility to meet an attacker anywhere on fronts of increasing scope. The Vickers, with its water cooling system, simply couldn't keep pace. When Hiram Maxim invented his automatic machine gun, it replaced another weapon that had gained only modest favor amongst the militaries of the late 1800s. The Gatling gun.
This is not a machine gun that, as we would describe it today, but we would call it a manually operated machine gun with a rotating cluster of barrels and some sort of feed device for the ammunition sitting on top. It's a machine, an engine that fires more than one shot, in this case by turning a crank.
Gatling's 1862 invention had failed to capture the hearts of the Army in its day. But when modern electronics and hydraulics were applied to replace the manual crank handle, and it was given modern armor-piercing rounds, it became the ultimate expression of the original, a 7-barrel machine cannon of devastating power. Like so many modern weapons, the GAU-8 was designed in 1970 with a particular Cold War what-if scenario in mind. In this case, it was, what if the Soviet tank forces just happened to come over the horizon? The Americans decided they would need a fast, highly mobile anti-tank weapon to defend against the possibility. And when the GAU-8 was found to be effective against heavy armor, it was given its own high-speed delivery mechanism. The Fairchild Republic A-10 Thunderbolt II, commonly referred to as the Warthog.
These things would scream in overhead and just destroy the armor, limiting the need to engage them tank to tank or to use anti-tank weapons, infantry anti-tank weapons. In practice, of course, the Cold War did not go hot. As an anti-tank tool, it kind of fell by the wayside.
And the GAU-8, along with the Warthog, might have passed into the footnotes of history like the Gatling gun had it not been for the Gulf War, where it was used against Iraqi armor with devastating effect. Very quickly, it was realized it could be an immensely capable close air support platform.
Not only will it penetrate tremendous amounts of armor or cover or anything you put in front of it, the energy being put forth by this is just so tremendous.
The Avenger has an astronomical maximum firing rate of up to 4,200 rounds per minute. That's roughly 70 rounds a second. And its armor-piercing rounds are lethal.
So it's projecting these huge 30mm in diameter shells, which are about yay long, and contain an immense amount of explosive potential. Everyone who's been in service anywhere near it loves the thing, and anyone who's faced it, I imagine, has feared it.
The GAU-8 Avenger is the pinnacle in the development of the machine gun. A line drawn from the defensive trench emplacements of World War I to close air support actions. And like all machines of war, they continue to adapt and evolve. The most fragile piece of equipment on any battlefield is the soldier. And for centuries, militaries have sought ways of protecting that asset. Body armor is nothing new. We are all familiar with the suits of armor worn by the knights of the Middle Ages. In the 20th century, the idea of offering protection to the enlisted man began with the issuing of simple steel helmets in World War I. But there's only so much you can get under a steel helmet. In World War II, air war resulted in huge losses of aircrew, who were quite literally sitting ducks for anti-aircraft fire. From a growing need to defend the undefended came the genesis of what we now call the bulletproof vest.
There was something called a flak jacket, and that was kind of the original name for a bulletproof vest. Aircrew used to wear these nylon vests which had these little 2-inch steel plates which were interwoven, and they would provide protection, as the name implies, from the flak, from the fragments from anti-aircraft munitions.
But they were bulky and extremely heavy. A problem solved in the early 70s with the discovery of Kevlar, a lightweight polymer 5 times stronger by weight than steel.
Over time, ballistic protection that was being offered to troops was getting better and better, and at the same time, the burden to troops was becoming less. So the vests themselves were getting lighter.
More protection, less weight. And as that evolution has continued, the bulletproof vest has been renamed. The Improved Outer Tactical Vest, or IOTV, is the very latest in troop protection. A medium-sized IOTV weighs 1.6 kilograms, down from 10 kilograms for a World War II flak jacket. Fully equipped, it has soft armor panel inserts, 4 silicon carbide ballistic plate inserts front, side, and rear, and collar and groin protectors. It is also designed with quick release and medical access features.
If the soldier gets into a very difficult spot, like underwater, then the individual can very quickly release the armor packs, and that gives them more mobility.
Mobile, light, and strong. A fully equipped modern vest can withstand a 3006 Springfield M2 armor-piercing round at normal range. But body armor is designed for a very specific task. Disposing of bombs and the increasing use of IEDs calls for protection that is quite different from taking an impact from a bullet. Most people wearing bulletproof vests in combat will probably be shot at from some distance, with a projectile optimized in shape to penetrate materials, a known threat. This is not the case for individuals attempting to disarm an improvised explosive device, a landmine, or an unexploded warhead. Up close and personal, the soldier will potentially be exposed to fragments traveling at incredibly high velocity, possibly even 12,000 to 15,000 meters per second as they're accelerated by the explosion. But that threat can be countered by the advanced bomb suit.
With a bomb suit, you've got to deal with a much more intense threat. It's of paramount importance to use thick materials that are able to deal with the loading that you get from an explosive blast.
In the aftermath of the London Blitz, bomb disposal teams worked largely unprotected when neutralizing unexploded ordnance. In the decades since, suits have evolved to become sophisticated pieces of military equipment, designed to withstand extreme force while allowing the wearer clear vision and mobility.
Bomb suit is generally made from multiple materials. So we would use high-strength steels or ceramics to deal with the fragments that you would get from an exploding munition or an exploding IED. And we use high-performance fibers such as Kevlar. And we use heat-resistant fibers as well, so fibers that are able to deal with the heat of an explosion.
All of these materials combined can offer protection from the shrapnel of the explosion. But it does little to defend against the shock of the blast.
So we use foam, and what the foam does, it mitigates the shock that you get from the explosive blast as it transmits from the bomb suit to the human body. And that increases the level of survivability for the occupant.
Every battle is an arm wrestle, an examination conducted by an attack on a defense. And the history of war is the story of the evolution and adaptation of offensive and defensive tactics and the machines used to fight them. The IED has changed the nature of warfare, and tactics and equipment have evolved to defend against it, just as they have in every aspect of warfare. And they will continue to do so.